So we're done with derivatives. Kind of. We'll be using derivatives. But tangent slopes, stuff like that. Changing gears. Okay? We're going to start our changing of the gears by talking about antiderivatives. Okay? All up until this point, we've been taking a function. It's got a shape. We've been finding a tangent slope generator. Okay? So we can find tangent slopes, locations of horizontal tangents, all that fun stuff. Find the instantaneous rate of change of the function. In this unit, we are going to be taking the tangent slope generator, and we're going to go backwards, and we're going to find the function. Okay? So I'm going to give you f prime. You're going to give me f. I'm going to give you dy dx. You're going to give me y equals. That's it. Okay? We will find that this thing called the antiderivative is going to be very, very useful with other applications. But for right now, and it'll be very, very useful when solving a very, very major concept in calculus. But for right now, all we're going to do for this entire unit is I'm going to give you f prime. You're going to give me f. Okay? Now, before we get into this antiderivative, let's make sure we remember how to take a derivative. Please take the derivative of all of these functions. Change this to a 3x squared. Okay, what is f prime given f? Go. Pretty incredible that this is like second nature to you guys now, especially this power rule, paying special attention to this power rule. Like if I told you at the beginning of the year, like what is the tangent slope generator, it's like you would have no idea what to do. But like the whole process of like taking 3, bringing it down, multiplying by 5, subtracting 1, this is like second nature to you. You just know like 15x squared 6x. You just like see it. You don't even have to think about it, which is cool. Okay, we're going to use that kind of instincts now because I'd like you to go backwards. I would like you to take this f prime and tell me what is f. If f prime is 4x plus 1, could you write down f whose derivative is 4x plus 1? See if you can do that. Good. Yeah, there we go. We might be thinking, it's got to be x to the 4th, right? X to the 4th. But then I think a little bit harder. I'm like, wait, hold on. If I take the derivative of x to the 4th, I don't get 4x, I get 4x cubed. It can't be x to the 4th. It's a good thought. It's the right idea. But maybe we think, you know what? Maybe let's not think about the coefficient first. Maybe let's think about the power first. I'm going to have something other than x to the 4th, so that when I take the derivative of it, yeah, good. Yeah, good. Good. You have x to the 4th. See if you can fix it. See if you can fix that. Not x to the 4th. All right, if you're not sure what it is, check with your neighbor. What about 1? Is it 0? Check with your neighbor. Most of you have it right. There's some of you that just need to come around for this first one. There you go. There we go. We realize we need x squared because I bring the 2 down and then I subtract 1, that's x to the first. But I need a 4, which means I need a 2 here too, so that 2 times 2 gives us 4x. Then for the 1, the derivative of 1 is 0, yes, but the derivative of x is 1. So 2x squared plus x. If you got that, very good. Let's try x squared. Let's try sine x. Let's try 5, and let's try 0. Very good. You tell me. I really like what we're doing here. We're realizing, okay, x cubed is what I need, but I can't just have x cubed because when it comes down, and I have 3x squared, I need a 1/3, which is very, very good.
Are we going to have to do plus c in here?
Now, I know the derivative of sine is cosine, but if I go opposite, I'm thinking, wait, the derivative of cosine is negative sine. I got to have a negative in front of this. So if you figured that out, very good. You're going backwards. You have the right idea of things. We know that 5x, its derivative is 5. What's derivative is 0? What'd you put, Mr. Bachelor? Yeah, like 16, 1, 5, another 1, another 5, 2, I like that, 4, numbers, anything, pi, derivative of pi, 0, e, the derivative of e, 0. We are going to use, my friend, c. C is a constant. C is any number. Well, my friends, since the derivative of a number is 0, turns out all of your answers for these 4, they were not entirely correct. Discuss with your neighbors, why weren't these entirely correct?
Because you can still like have probably because I use the add numbers.
Yeah. Very, very good. It's because I can add any number to this, and its derivative is still 4x plus 1. I could add any constant, whether it's positive, it's negative, it's large, it's small. Any number can be added to that, and its derivative is still going to be those f primes shown on the left. So, my friends, we are going to need to understand that and incorporate that when we're going backwards. We're going to need a plus c. And now, this is correct. Now, what is c? I don't know. Depends. It could be something. It could be nothing. It depends on what other information we're given. Right now, we're just told, like, what could a function be whose derivative is 4x plus 1? Well, your function could be 2x squared plus x plus anything, and its derivative is 4x plus 1. So we solved the problem. We are good. Now, if we were given more information, if we were told, hey, give me a function that has the point 1, 2, whose derivative is that, we'd be able to find this specific value, whether it is a very specific value or if it's just 0. Okay? And that's what we're really going to be doing. All unit is just finding f, given f prime, and some more information. But before we do that, we got to make sure we understand taking antiderivatives. You got one more to do for me. Try this one. Go ahead. We got the basics down. You understand the plus c. Let's do x squared sine x. Ready, set, go. X squared sine x. We already took the antiderivative of x squared. Okay, so we feel good about that. 1/3 x cubed. Took the antiderivative of sine, so that's negative cosine. And then I think, wait, that can't be correct. Why isn't that correct? Because then I have to use the product rule if I took that derivative. So if I take that derivative, I'm not going to just get simply x squared sine x. So it's actually not this. Oh gosh, what do I do? Turns out, you're not going to know what to do. And unless you take BC calculus, you won't know how to take that antiderivative. Antiderivatives are not as easy as derivatives. Hold on, let me freeze. Actually, that's not going to work. I'll just open up Wolfram right away. Watch. Let's go to Wolfram. Antiderivative of x squared sine x. It is actually 2x sine x minus x squared minus 2 cos x plus a constant. Would you have ever guessed that it was going to be that? No, no. So there's two things I want you to know about antiderivatives. One, you got to have a plus c. You need a plus c because the derivative of c's are zeros. And the other is it's not as simple. It is not going to be easy. There is no antiderivative product rule. There's no antiderivative quotient rule. There are techniques to undo the chain rule, but our functions have to be set up in a very, very specific way to utilize these techniques. Okay, and we'll learn those techniques in the second semester. We're going to keep things pretty simple in this semester. Okay, power rule, antiderivatives of basic trig functions, antiderivatives of 1 over x, e to the x, and then like constants kind of being involved in those e to the x's, 1 over x's, sine of x's. Okay, now there's new notation. We say f is the antiderivative of f prime. There's a new letter that we'll use for the antiderivative of f. Capital F, I'll call it big F. Big F is the antiderivative of regular f. Okay, so this is just a new notation letter we are going to use. If we want to take the antiderivative of f, we get big F. The derivative of big F would be f, the derivative of f, f prime. We cannot take antiderivatives past big F. There's no double big F. We're just going to stop at big F. We would use another variable if I wanted to take the antiderivative of big F. Okay? We will go over the specific rules after lunch. All right, so we have a good sense of how to take an antiderivative. You guys are just doing it. Like, you kind of figure out, like, all right, what, it's almost like a Jeopardy question. The answer is the question. You know, it's like, what function can I take the derivative of to get what I have? All right, so let's be a little bit more specific, though, and let's talk about rules. So if you have a function that's 0, big F, its antiderivative is a constant c, which is why we will need a plus c after every single antiderivative, because we could have a constant after the derivative of 5. Not just 5x. 5x is in the only function whose derivative is 5. 5x plus c has a derivative that is 5. Okay, please take the antiderivative of x to the 4th. The antiderivative of x to the 4th. Now, after you take the antiderivative of x to the 4th, see if you can come up with yourself the power rule for an x to the n. So if it was n, then 4 would stay 4. But you made 4 5. So what did you do to n? Okay. Yep, you're good. Then, if it was 1 over n, and n is 4, you'd have 1 over 4. But you have 1 over 5.
It's the same thing right here.
Same thing right there. Okay, we realize we have to add 1 to this exponent to get x to the 5th. Okay? But then I know when I take the derivative of x to the 5th, it'll be 5x to the 4th. And I don't want 5x to the 4th. I want just x to the 4th, which means I need a 1/5 here. So what we end up doing, and this is the procedure, and let's see if you got it, is we take our power n, 4, we added 1 to 4 to make it 5. We then multiplied by the reciprocal. I'm not multiplying by 1 over n because that'd be 1 over 4. I'm multiplying by 1 over n plus 1. And I'm adding a c. So the process is, and this is kind of counter to the derivative process. Derivative process is take the 4 down first and then subtract 1. The process for antiderivatives is add 1 to the power then, after you've added 1 to the power, multiply by the reciprocal. Of that new power. Okay? Now, if I have a constant times a function, we can kind of just see it'll make sense. Its antiderivative will just be the constant left alone. I don't have to take the antiderivative of the constant and then times the antiderivative of g. So examples of this will be like this. I do not have to say, oh, the antiderivative of 5 is 5x. Then the antiderivative of x cubed is x to the 4th times 1/4. No, that's silly. And we know that we would just take the antiderivative of x cubed using the power rule. And then we just have to incorporate the 5 when I multiply by the reciprocal. So see if you can take the antiderivative of 5x cubed. That's it. Add 1 to the power, then multiply by the reciprocal. You can do it, and it just involves practice. And once we've practiced this, we'll be good. 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 X to the 4th, multiply by the reciprocal, and then multiply by 5. Some of you will be comfortable doing this all in one step. Until you're comfortable with it, I advise you add 1 to the power, multiply by the reciprocal, then worry about the 5. And that turns into 5/4 x to the 4th plus c. Okay? Please do the next 4. If you're not comfortable with doing it all at once, I'd advise you add 1 to the power, multiply by the reciprocal, then worry about the other constant that you can multiply in at the end. Your first one should be 1/15 x to the 5th plus c. Okay, but go ahead and do the other ones. And check your answers with a neighbor, please. We should get 3 halves x to the 4th plus c. If I have a negative power, it's okay. Add 1, make sure it's not -3. Multiply by the reciprocal. Well, that's just going to be like -1. So we'll have -1/3 x to the -1st plus c. X has a power. Its power it's 1. Add 1. Multiply by the reciprocal. Okay? You were figuring it out yourselves, but this will be a little bit more efficient instead of having to use your brain, honestly, using the rule. It'll just be a little bit more efficient than trying to figure it out. If you have multiple things added, just understand that you don't need a plus c after everything. You know, I'm going to take the antiderivative of g plus the antiderivative of h, and I just need 1 plus c afterwards. Okay? Because if I have a bunch of plus c's, well, you can just add them together and you just have a plus c. So after you take the antiderivative of 5x cubed, 12x squared, and x, and 3, then add a plus c. Okay, I'll kind of work through it one step at a time and then show the simplified form after. See if you can do it. I mean, this is good stuff to practice. This is your first time trying this. So if you're just copying down, try not to. Okay, the answer's up there if you want to check. Blue and red make green. That should be green. Upsetting. Sometimes they're good about adding colors. Blue and yellow. There you go. What's blue and red? Purple. That should be purple. I teach math. I do have a kid, though. I should be better than that. All right. Trig rules. What you will find is that I can't just give you any trig function. It has to be a very specific trig function. Like, I can't give you tangent. You do not know a trig function whose derivative is tangent. Think about it. Okay, no, it's not sine, cosine, it's not tangent, it's not cotangent, it's not secant, it's not cosecant. We're going to figure tangent out later after we learn a different rule. Sine times cosine, you will not be able to figure that out. Okay? It has to be very specific ones like, oh, I know the derivative of tangent is secant squared. Now, I'm going to throw some numbers in there just so we know that, like, if you see a number before the cosine, the antiderivative of 3 cosine x is not 3x sine x. We know that that's not right because I'd have to use the product rule because of the 3x and the sine x. Constant, just leave alone. If I have 3 cos x, I know the derivative of positive sine is positive cosine. I'll have 3 sine x. Okay? All right, what's the antiderivative of 2 sine x? Exactly. Negative 2 cos x, or 2 times negative cos x, because the derivative of cosine is negative sine. This is going to be tricky for many of you, keeping track of derivatives and antiderivatives, because all of a sudden we're going to be going both ways. It's like you got to remember the derivative of sine is positive cosine, but the antiderivative of sine is negative cosine. So it gets all kind of confusing in your head. Keep the derivative way in your brain. Don't try to memorize the antiderivatives, or they're going to really get screwed up in your head. The derivative of secant, you remember, is secant tangent. If there's any number in front of things, don't worry about it. The derivative of cotangent would be negative cosecant squared. Just have this 3 right in front of it. Put a negative so that the derivative of negative 3 cotangent is positive 3 cosecant squared. The derivative of cosecant is negative cosecant cotangent, so I'm going to have to do the opposite for this as well. Okay, but they really have to look very specifically for you to be able to take the antiderivative. You don't know what the antiderivative of tangent is. You do not know what the antiderivative of cotangent is. You don't even know what the antiderivative of secant is, though you could, I don't know if you can figure it out, actually. You can figure it out. You can figure it out. Okay, cool. Now, we remember notation for derivatives was d dx. D stand for, take the instantaneous change or take the derivative. Take the derivative. And the dx stood for like with respect to x. And the goal was to find the change in y over change in x, but this also means with respect to x. And you would take the derivative using your derivative rules, you'd get 6x. Okay? The notation for an antiderivative is this tall, skinny s, which is called an integral. We will be using integrals for other things besides antiderivatives in this class. We'll get there. But for right now, an integral means take the antiderivative. But again, we need this like with respect to x, because remember we took d dt a lot last unit. Find how we are changing at a moment in time. So we will put the with respect to x outside of it. This dx stands for with respect to x. We will not have to worry about like the antiderivative of 3x squared with respect to t, fortunately, in this class. If you go on to multivariable calculus, though, you will be taking the antiderivative of variables with respect to a different variable. But using your power rule, you will just get x cubed plus c, right? Add 1, multiply, so that's 3 times 1/3. Okay, so it's just x cubed plus c. What's important is that if there was anything else in here besides just 3x squared, like plus 2, you would need to use parentheses because it is kind of like, multiplication, kind of. Just like it is kind of multiplication over here. So just make sure you use parentheses so that you understand it would be x cubed plus 2x plus c. It's just proper notation. It's not that important, but it is proper notation. Okay? Parentheses needed. All right. So, if you see this, first of all, Mr. Messner fails. There should be parentheses here. It's in between the integral and the dx, just like the d dx parentheses. Okay. You're just going to read this as take the antiderivative. That's it. Okay, integral antiderivative with respect to x. So I'll just do them quickly. This is 1/3 x cubed plus 1/2 x squared plus x plus c. And it's just equals. There's no f of x equals because we don't have like an expression f equals or f prime equals. Fractional powers, x to the 1/2, x to the 1/3. We're going to have to add 1, then multiply by the reciprocal. This is good. So I start with 1/2, add 1. Okay, please add 1 to 1/2. I get x to the 3/2. Now, for all the other situations, we always put 1 over that new exponent, but it's not necessary here. This is why I said multiply by the reciprocal. We know a reciprocal of a fraction is just going to be 2/3. So don't put the 1 over. Just put the reciprocal 2/3. Whatever. Okay, so see how that's different. If you have a fractional exponent, boom, just flip the exponent after you add 1. We got to do it for x to the 1/3. So I'm going to add 3/3 to 1/3. That'll turn into x to the 4/3. Don't times it by 1 over 4/3. Multiply by the reciprocal. So just flip it. 3/4 plus the c. If you see nothing, assume there's a 1 there. Okay? Reminder, just like the power rule for derivatives, the power rule for antiderivatives do not work in denominators. Power rules work in numerators. Work in the numerator. So you will not say this is like 1 over x to the, 1 over x to the 4th times 1/4. Wrong. You would instead rewrite this as x to the -3rd and then take the antiderivative. Go ahead and do that. Same rule applies. It's just a power, just a number. Add 1, multiply by the reciprocal. That's it. Add 1, multiply by the reciprocal. That's it. Yep. Just be careful where you put the x to the power. If I add 1, I get x to the -2nd. I multiply by the reciprocal, I get -1/2 x to the -2nd plus c. To rewrite that, you could write it as 1 over 2x squared plus c. Okay, so like x to the -2nd is in the numerator. You can move it to the denominator by making that power a positive power. All right, try with 10x to the 4th, please, or 10 over x to the 4th. These are yours. Homework and notes. Okay, cool. X to the -3rd times -1/3 times 10 plus c. I get -10 over 3x cubed plus c. All right? If you see quotients, if you see products, like this, I'm going to throw another one in here, like this. You can't use the quotient rule. You can't use the product rule. There is no quotient rule for antiderivatives. There's no product rule for antiderivatives. You are going to have to simplify first. Always, always, always. You see that there are two things divided by one thing. I can divide both of those things by that x squared. Turns it into 3x squared plus 2 over x squared. I can write it as 2x to the negative first. Parentheses. Not needed here because it's a fraction. Then add 1, multiply by the reciprocal. That cancels. Add 1. X to the negative first, multiply by the reciprocal, negative 2x to the negative first. We need to remember, when we divide by fractional, or just when we divide in general, we're subtracting. X divided by root x becomes x to the 1/2. If this is x squared divided by root x, this would be x to the 3/2. That's 4 halves divided by, or 4 halves minus 1/2. And then 1 over root x would be x to the negative 1/2. I would then take the antiderivative of that. I changed this to an x squared so that it's x to the 3/2. Add 1, multiply by the reciprocal. Add 1, multiply by the reciprocal, plus a c. Sorry if my notes are a little cramped. You guys have more space to make sure you spread things out and show more things, okay? Sine x over cos squared x, I have no idea. Simplify first. I could write this as sine x over cos x times 1 over cos x, which then can be written as tan x times secant x. What's the antiderivative of tan x times secant x? Stay with me. Which trig function's derivative is tan x times secant x? What is it?
Secant.
Thank you, Mr. Kingsley. Secant has the derivative of secant x tangent x. You got to remember these. Just showed up right there. Okay, so that was like no quotient rule. Simplify the quotients. There is no product rule. I threw this one in. This is an extra. Please write this in to your notes. You either need to distribute. This is easy to distribute. Or, square things so that you can use the power rule. This becomes x to the 4th plus 4x squared plus 4. Antiderivative, x to the 5th times 1/5 plus x cubed times 1/3 plus 4x plus c. Here, x to the 4th times 1/4 minus x cubed plus c. Okay, so we pretty much know almost all of the antiderivative rules that we need to know. We're going to learn like one extra one next class, and we're going to talk about like e's and 1 over x. So now that we know most of what we need to know, why don't we just start doing what our really end goal is for all of our questions in this unit, is going backwards. If I give you f prime, can you give me f? And can it be a very specific f? This situation is called a differential equation. A differential equation is just like f prime equals dy dx equals. That's a differential equation. We are going to be asked to solve differential equations. When you're asked to solve a differential equation, it just means like go backwards to find f. That's it. The solution to a differential equation is a function. It's f. Might be a function, might be a non-function, but it is an equation that satisfies the conditions. So like in the previous kind of examples we've done, if I gave you f prime, you could easily tell me what f is. Please find what f is. Write that down. Okay, please write f of x equals. A lot of us don't like to, but we need to. F of x equals 2x to the fourth plus 5x plus c. Don't forget your plus c. This, my friends, is what we call a general solution. It's a general solution because it has a plus c. That's not our ultimate goal. Our ultimate goal is to find a very specific function whose derivative is 8x cubed plus 5. And the specific function will be found by utilizing this extra piece of information. Okay? This is called like an initial condition. We are told, hey, the function that we want to try to find, this going backwards function, needs to have the point 1, negative 4. Well, we are going to use that point to find c. And then what we will have is a specific solution, a specific function who has this derivative. We will call it a particular solution. All I have to do is plug in 1, 2 plus 5 plus c. This should equal negative 4. I get 7 plus c equals negative 4. C must equal negative 11. Now, that's not my solution. My solution is the equation f of x equals 2x to the fourth plus 5x minus 11. This is our goal, finding this particular solution. This is what we call our particular solution. C was found using your info. Okay? All right, your turn. Please solve the next differential equation, f prime equals 2x plus 3, with the initial condition f of 2 equals 3. Take the antiderivative of 3. This is where things get crisscrossed. If you take the derivative of 3, it's 0. But if you take the antiderivative of 3, it's 3x. Here, c is negative 7. My solution is x squared plus 3x minus 7. That particular function has the point 2, 3, and the derivative 2x plus 3. Okay? All right. Well, those seem easy enough. Why don't I give you a second derivative and ask you to find f of x? The key to this is actually to notice the information that you have. You have information about a derivative at a point and another point on the original function. Go one step at a time. Don't go straight from f double prime all the way to f really quickly. One step at a time. Go from f double prime to f prime. You will have a c in f prime. The antiderivative of 2 is 2x plus c. Don't forget your plus c's, even when you go from f double prime to f prime. Find that c using f prime of 0 as 1. That is a particular f prime. Now go from f prime to f. Okay? Now, the next one I'm going to change. Cross off this information. You get x squared plus x minus 8. Cross off this information. I'm going to tell you to find the solution to the differential equation whose second derivative is 3 and that has a horizontal tangent at 2, 1. All right, let's go from f double prime to f prime. Find f prime. Easy, right? 3x plus c. What information can I use to find this c? Discuss with your neighbors. What information can I use to find c? If you're thinking, plug in 2, set this equal to 1, nope. Horizontal tangent means our derivative at 2 must equal 0. So if you had that thought, very, very good job. We are translating this statement into kind of calculus notation, calculus ideas. So I'll get f prime of 2 is equal to 6 plus c, and that equals 0. C's got to equal negative 6. So that gives me a particular f prime. Let's go find f. Now I do have the point 2, 1. That's f of 2 equals 1 point I can use. Might look like it'll be messy, but it works out nicely. Three halves times 4, that's going to be 2 times 3, which is 6, plus negative 12 plus c equals 1. I get negative c plus c equals 1. I get c is equal to 7. F, therefore, is 3 halves x squared plus negative 6x plus 7. Okay, last one. If you have trig functions, don't worry, one step at a time. F prime would be negative cosine x plus c. Throw a 2 there just for fun. Remember, it's just going to be that number there. Don't put 2x cos x, okay? F prime of 0 is 1. So negative 2 cos 0 plus c has got to equal 1. Cosine of 0 is 1. I hope we all know that. We'll get c is equal to 3. So that's f primes particular. And then we'll take the antiderivative one more time. And we have the initial condition f of 0 equals 5. Go ahead and finish that off. I'll have negative 2 sine x plus 3x plus c. F of 0 would be 0 plus c equals 5. I got it. Negative 2 sine x plus 3x plus 5. Okay? Okay, not bad. Like, this should seem doable for us. This isn't that tough. There's actually not that many applications of antiderivatives right now that we'll have to worry about it. There will be more in the future.